All right, so we are here on day 19, and if you are not in class today, then you should be watching this lecture in lieu of being in school. If you were in class yesterday, obviously we already did ranking test day 18, so you do not need to worry about that. But today we're going to be discussing vector methods in physics and how we utilize vectors. And you guys do this in pre-calc. You do a lot of vector stuff where you do like heading and bearing, and three rangers spot a forest fire, and a plane flying southeast receives a stiff westward tailwind, right? So there's all these concepts that are physics related that utilize vectors. We are not going to be getting too deep into that, but we do need vectors for just a couple of concepts. And the big thing that we're going to be doing is we're going to be able to use vectors to describe displacement, velocity, and acceleration, which we've already been doing. And now the more important thing is we're going to understand what components are and how it relates to vectors. So under this little key formula area here, I have a velocity vector. And this velocity vector is moving up and to the right. So before we would say it's moving in the positive x direction and it's moving in the positive y direction. Well, if I just give the velocity, I have to be able to break that into its x component and into its y component. And that's pretty much the important thing about today. Noting that this right here, this corner, is in fact a right angle, we can really easily break this velocity into x and y components. And that's going to be a big part as we go through chapter 3, because chapter 3 is all about applications of kinematics and how we're going to use uniform and non-uniform motion to solve problems. So we need we need the concept of breaking things into components for things like projectile motion and acceleration down a ramp. So we'll be doing that throughout the course of this chapter. Now, your homework today does expand through problem number 70 in your problems packet. So we've already covered chapters 1 and 2. Chapter 1 was a really easy introduction into a couple scientific things and essentially putting numbers to motion. Chapter 2, we got into the concepts of uniform and non-uniform motion, and we built a bank of equations that we can use as well to help us describe that motion. Chapter 3 is all about applications of uniform and non-uniform motion. So we're going to be going through the first big chunk today, which is my summarization of vectors, but we're also going to get into projectile motion, motion on a ramp, and a couple other relative motion, and just a quick look at circular motion. So pre-lecture video 1 is on vectors in motion. You can feel free to check that out. He does a couple demonstrations to help visualize and explain vectors. And I'm paraphrasing the first 3 sections of notes. So you can go through and read sections 3.1 to 3.3 in your book to review vectors. If you haven't learned them yet in pre-calc, I'm going to teach you the bare minimum that we need. We only need to do a few example problems to cover these sections. And then tomorrow we have a lab. So we'll have it's a classic. It's called the Vector Treasure Map, and we'll be looking at that tomorrow. So vectors, we've already been using vectors. We know that a vector is a quantity with both size and direction, so both magnitude and direction. So here below, I have a picture of a velocity vector. The size of the vector, how long it is, represents its magnitude, and the direction that the arrow going represents the direction of the vector. So this is a velocity vector. It's going 5 meters per second, I don't know, 30 degrees north of east, right? So here is my positive x. So it's going both positive x and positive y at the same time. So the direction is not straight x or straight y. It's a little bit of both. And that's going to be an important concept as we go through and learn about things like projectile motion. So if we don't have an arrow, we call that scalar, and then we're strictly looking at the object's speed. So it's the magnitude of velocity, which is just 5 meters per second. The magnitude of a scalar, or the magnitude of a vector, which is a scalar, can never be a negative number. So I can have a displacement of negative 5 meters, but I can't walk a distance of negative 5 meters. It seems really trivial and really like precise, but we're just trying to make sure we have the right vocabulary as we're going through here. We've also looked at displacement vectors. The displacement vector connects your initial position to your final position, regardless of the actual path. And we talked about that before. We talked about that when we talked about distance versus displacement. So two vectors are equal if they have the same magnitude and same direction, regardless of the individual starting points of the vectors. So here, one vector starts at Becky's house, the other vector starts at Sam's house. So they have different locations, but they have the exact same magnitude and direction, so they are the same vector, even though they start and end at different locations. So we're going to talk mainly about how do we add vectors today. So in this example, the net displacement, if I go from point P to point Q and point Q to point S, the net displacement is C. Okay, so I go from P to Q, Q to S. My resultant vector, my net displacement vector, is C from start to finish. And in this case, it's really easy. I have 4 meters east, 3 meters north, and I can solve for the magnitude of C using Pythagorean theorem. I can solve for the angle using tan inverse. But that's an example of individual displacement vectors. So we're going to talk today about different ways that we can add these vectors together. So how do we solve vector problems? Well, the one that we just did, and we'll take a look at it again, is known as the head-to-tail method. We also have an algebraic method, which is where we break things into components. This is extremely important because we have to be able to break vectors into components. Now, then we can look at all the x's and all the y's and add them up together. The last method is graphically, which we will also be taking a look at tomorrow during the lab. The lab tomorrow talks really about algebraic and graphical. But graphically means that we're going to plot it on a piece of graph paper and be very precise. Okay, so the head-to-tail method, you draw the first vector, you place the tail of the second vector on the tip of the first vector. So that's essentially what we just looked at with going from P to Q and Q to R or S, whatever it was. And then we draw an arrow from the tail of A to the tip of B, so the starting point to the ending point. And we can use Pythagorean theorem and tangent to solve for this. These work great for easier problems, but not for traveling at angles. So let's take a look at an example problem. We have a small plane is 100 kilometers due east of Denver. After 1 hour of flying, it's 200 kilometers due north of Denver. So represents here, oh man, let me read, okay, I can't. Okay, that represents Denver. Okay, Denver's right there. Sorry, I don't have my pen on me today. So I start 100 kilometers due east, and I end 200 kilometers due north. So what's the plane's velocity? Well, I went from my starting point to my ending point, so that is my resultant vector. And this is the head-to-tail method. If I could have also went from my starting point 100 kilometers west and then 200 kilometers north, and this makes a right angle right here. So my resultant vector, I can use the Pythagorean theorem to solve for, and I can get this angle right here. So let me show you a better picture of it. So here's a better picture of it. I started 100 kilometers due east. I ended 200 kilometers. Sorry, it looks like I cut that off. I ended 200 kilometers due north. So my displacement is going to be the square root of the sum of 100 kilometers plus 200 kilometers, which is about 223.6 kilometers. Velocity is just distance over time. So my distance was the 223.6 kilometers. The time was 1 hour. So my velocity was 223.6 kilometers an hour. Now, Velocity has to have magnitude and direction. In this case, I'm not going 223.6 kilometers an hour east. I'm going some angle that is northwest. So if I use tangent, I can solve for the angle, which I did. It's the tan inverse of opposite over adjacent, and I get 63.4 degrees. So my answer here is I'm going 223.6 kilometers an hour, 63.4 degrees north of west. You have to have some type of reference angle in order to absolutely define the direction. I think in pre-calc you guys do heading and bearing. That gets a little confusing. So if you just say 63.4 degrees north of west, so it's up from west, that's totally fine. That's nice and easy, and it's an easier way to keep track of it. Okay, the next method, and this is the important thing to get out of today, is the algebraic method. Now, the algebraic method is great anytime I have vectors that are going at angles. So we need to assign a coordinate system, and then we break our vectors into x and y components. We can add all of the x components together and add all of the y components together to get our resultant x and our resultant y, and then we can get our resultant vector using those components. So this is useful if when we have a lot of vectors or a lot of tilted vectors. So here's an example. I'm flying a plane at 250 kilometers an hour, 30 degrees north of east. And I'm flying against a wind that's traveling 10 kilometers an hour, 15 degrees south of west. What's the resultant magnitude and direction of my flight path? So I'm flying at, here's me flying, 30 degrees north of east, 250 kilometers an hour. Okay, so here's 30 degrees. So that means I have a velocity in the x direction and I have a velocity in the y direction. All right, and then there's a wind that's 15 degrees south of west. So here is, and my angle right there is 15 degrees, and that's 10 kilometers an hour. Okay, so I have that velocity that's also in the x direction, and in this case it's the negative x direction, and it's the negative y direction going against me. So I need to break my plane's velocity into components, and I need to break the wind into components. And if I add all them together, I can get the resultant vector. So let's see a better picture of it. Okay, so on the left here, I am breaking my vectors into components. I was going 250 kilometers an hour, 30 degrees north of east. Well, then I have an x component. Technically, I'm going in the positive x direction at 216.5 kilometers an hour. And I'm going in the positive y direction at 125 kilometers an hour. Similarly, I have my my wind. My wind is going in the x direction, or the negative x direction, at 9.66 kilometers an hour, and we're going in the negative y direction at 2.59 kilometers an hour. So I am going with my plane. I'm traveling north and east, but I have a wind that is going south and west. So my resultant velocity is going to be the sum of all of those velocities. So here I have a table where I add them together. I have my two x velocities, I have my two y velocities, and I add them together. My x resultant is the sum of my x's, my y resultant is the sum of my y's. Then I can utilize that, and I can make a resultant x and a resultant y, and use Pythagorean theorem to solve for my resultant velocity, which in this case ends up being about 240.35 kilometers an hour. And I can use my tangent to again solve for my resultant direction, which is in this case 30.62 degrees north of east. So we can utilize breaking vectors into components, adding all the components together, adding all the x components and adding all the y components to get a resultant x, a resultant y, and then I can use the x and y to get my absolute resultant vector, both magnitude and direction. And that's the algebraic method. What do you really need to be able to do at the end of today? You need to be able to do this. Take your velocities and break them into components. And if you can do that, you'll be all right. You need to be able to. Now, the last method that we can use to solve vectors, and we'll take a look at this during class tomorrow, is the graphical method. And the graphical method just says if I start at some point and I travel 5 spaces east, 5 spaces north, if I travel 3 spaces 45 degrees north of east, I take a protractor and I literally draw this correctly. I draw all of my vectors correctly, north of west, whatever. And I add up and I put all my vectors head to tail, and then I have one resultant vector that goes from start to finish. So we'll take a look at this for the treasure map concept tomorrow with lab 1.6, the vector treasure map. You can then if you draw everything absolutely precisely, you can draw a resultant vector and use the concept of the graph to help you explain or help you show what's going on. So not a very common method that we're going to use because it does require drawing everything to scale, but it is another way that we can do this. So for tomorrow, I have a scale map of the classroom that we can use to do a vector treasure map. So that was a quick overview of vectors, and specifically solving vectors when we have to break things into components. But I want to recap one thing. When I have a velocity vector, here's a velocity vector, okay? It has an x component, vx, and it has a y component, vy, if it's launched at some angle. Now, that vx, it's the adjacent, so we can use v cosine theta to get the x component. This y is kind of transferable. I can move it over to this side. So vy is v sine theta. You need to be able to break velocity into x and y components. This concept is going to come back in projectile motion, and it's going to come back in Unit 2 when we go talk about forces again and forces acting at angles. So this is a right angle right here, so I can use sine, cosine, tangent, and I can use the concept of SOHCAHTOA to solve for the x and the y components. That's the most important thing to get out of today. We need to be able to break vectors into components. And I know that's kind of a trig thing, but it's pretty quick for us, so that's where I'll leave it at for today. Please let me know if you have any questions. I know that was a pretty quick crash course. You're also welcome to watch the actual lecture from class, and maybe me going through the problems a little slower on the whiteboard might help you out a little bit, so feel free to check that out as well. Otherwise, have a great rest of your day, and we'll see you tomorrow for the Vector Treasure Map Lab.